So we discussed that for a reaction that has two reactants, the second order reaction, it is difficult to determine, to actually derive the rate law because the velocity depends on, velocity is increase of concentration of product over time. It will be equal to rate constant by the concentration of each of the reactants. So it's difficult to determine, to derive that rate law, but it will be easy if concentration of one, initial concentration of one compound, for example, was much higher than the concentration of another compound. And so if that was the case, we could, we know that we can assume that just a very tiny amount of reactant A is being consumed. And so the total concentration of the reactant A stays more or less equal to what we started with, because each reactant should be consumed in the same, like in stoichiometric amounts, right? So we can say that concentration of the reactant A doesn't change over time, and we can just focus on the change in the reactant B, correct? So we can treat this reaction as pseudo first order reaction because this constant is, this part is constant. So we can say that it's some kind of apparent rate constant. And the same can be said if we have the scenario in which the starting concentration of A is much lower than B. In this case, we can say that velocity is equal to K by concentration of A, which changes over time, but concentration of B stays more or less the same. And then we can determine the rate as a decrease in concentration of A over time, and that would be also pseudo first order in terms of A in this case, right? Another special case of, like, this is kind of a special case of the reaction which has two reactants, right? But another special case would be when the stoichiometry of the reaction is such that we have 2 moles of the same reactant reacting, right? So we'll have A plus A right here. Let me erase it a little bit. That translates also to the second order rate law because velocity, which is accumulation of product over time, is proportional to the square of the reactant concentration, because we need to react two molecules, two molecules of A need to react, right? And so we can focus on the following differential equation right here in order to derive the second order rate law. So we will do the same thing that we did for the first order. We will group everything that has the reactant in one part of the equation. And actually, I will leave my minus right here with it. And I will put everything that don't have the concentration of the reactant on the other side of the equation. Now I'm going to take that integral, right, from 0 to t. That means from the initial reactant concentration to some concentration that remains at time t. And that will be equal to 1 over A, concentration of the reactant, equal to 1 over the initial reactant concentration plus Kt. So this is our second order rate law. So if we plot, actually let's plot it not as a function of reactant concentration over time, but instead we will plot it. Oh, it doesn't draw. We will plot it. Okay, here you go. As the inverse reactant concentration over time. So we will start with, because it's the y-axis is inverse, our starting point is right here, and as the reactant gets consumed, its inverse function is accumulated. So we see increase, and the slope of the reaction, slope of that relationship is our rate constant, second order rate constant. And we expect the concentration of the reactant to drop twice at our half-life. Right? Or we also call it T1 half. And if we just plug 2 over the initial reactant concentration in the rate law, we will see that actually here we will have already tau, right? That tau is equal to 1 over K by the original, initial reactant concentration. So now, unlike in the first order reaction, when tau doesn't depend on the reactant, here we have inverse proportionality between tau and the reactant concentration, meaning that if we increase the original reactant concentration, our half of the reactant will be consumed in less time, which correlates with the rate being proportional to the concentration of the reactant.